I welcome you all to the second session of game theory. So far, in the game theory 1, we have discussed the solution of games with pure strategies where you could solve a game only when the maximum value for the maximizing player was equal to the minimax value for the minimizing player. In other words, the value of the game could be found out only when there was a saddle or equilibrium point, and that game was called a game with pure strategy. But when there is no saddle point in a game, then it is called a game with mixed strategy. In order to solve such a game, each player adopts the concept of chance move. Each player starts to play in a random manner and in such a way that his average payoff over a large number of plays of the game should be optimum, even though he may lose more in any individual play of the game. In other words, the player adopts a certain strategy for some time and then shifts over to another strategy and then after some time to third strategy and so on, so that the average payoff over a large number of plays of the game becomes optimum, that is maximum for the maximizing player and the minimum for the minimizing player. Now after going this video, you should be able to solve the game with mixed strategy, understand the meaning of the expected value or expected payoff, find the value of the game with mixed strategy. Now, what are the mixed strategy? If a player does not adhere to the same strategy throughout the game but mixes the strategies in such a way that his opponent is not in position to guess it, and moreover he himself does not know what his next move would be, then the game is said to be played with mixed strategies. In other words, a game with mixed strategies is the game where the saddle point does not exist. No pure strategy. So, mixed strategy for player X is a vector X from x1 to xm of m non-negative real numbers that satisfies the condition sigma xi for I varies from 1 to m is equal to 1, where xi may be interpreted as the probability with which player X chooses the strategy I. Similarly, a mixed strategy for the player Y is a vector Y from y1 to yn of n non-negative real numbers satisfying the condition sigma yi is equal to 1, where y may be interpreted as the probability with which player Y chooses strategy I. For this, we use the concept of expected value from the probability theory. In probability theory, the expected value of an event is defined to be the sum of the values of each possible outcomes of the event times the probability that the outcome occurs. Therefore, if player X chooses the mixed strategy X and player Y chooses the mixed strategy Y, then the outcome Aij will occur with probability Xiyj, since this is the probability of both the player X choosing the strategy I and the player Y choosing the strategy J. Thus, the expected value for the game is the sum of all the products of Xi, Aij, Yj. That is sigma j varies from 1 to n, I varies from 1 to m, xi, aij and yj. Now, a game with mixed strategy is generally solved by some of the following methods: algebraic method, graphical method, linear programming method. Here, we shall discuss the algebraic method. We discuss the method through an example. Let us consider a two-person zero-sum game with payoff matrix of order 2 by 2 for players A and B. In the given matrix, there is no one value which is the smallest value in its row and the largest in the column. There is no saddle point in it, and the game is not that of the pure strategies. That is, none of the players A or B would play the same strategy throughout the game, but they would resort to what is known as mixed strategies. That is, the player A would play each of his rows A1 and A2 for a certain portion of time, and the player B would play each of his columns B1 and B2 for a certain portion of time. Accordingly, if the player A plays the strategy A1 for certain time T1, then he would play his second strategy A2 for the remaining time 1 minus T1. Similarly, if the player B plays the strategy B1 for the time T2, then he would play his second strategy B2 for the remaining time 1 minus T2. The total time for the playing being taken as unity. This could also be interpreted in terms of the probabilities, as if the player A selects strategy A1 with a probability P, then he would play strategy A2 with the probability 1 minus P, since the sum of the probabilities is 1. Similarly, if the player B selects his strategy B1 with probability Q, then he would play his strategy B2 with probability 1 minus Q in the given payoff matrix. Let A selects the strategy A1 with probability P, and he would select the strategy A2 with probability 1 minus P. Suppose now the player B selects the strategy B1 and adheres to it throughout the game, then the expected payoff or expected gain to player A for this game would be an algebraic sum of the expected values of the two events, that is 25p plus 10 times 1 minus p. But if player B selects the strategy B2 and adheres to it throughout the game, then the expected payoff or expected gain to player A for the game would be 5p plus 15 times 1 minus p. Now, in order that the player A may be indifferent to the strategy B selects, the optimal plan for the player A should be such that 25p plus 10 times 1 minus p greater than or is equal to v, and 5p plus 15 times 1 minus p greater than or is equal to p, where v is the value of the game. If the inequalities are satisfied as equation, then we get this equation, and solving for p and q, we get p is equal to 0.2 and 1 minus p is equal to 0.8. Hence, the player A would select the strategy A1 with probability 0.2 and the strategy A2 with probability 0.8. Similarly, if the player B selects strategies B1 and B2 with the probabilities Q and 1 minus Q respectively, then the expected payoff or expected loss to player B when the player A adopts the strategy A1 throughout the game would be 25Q plus 5 times 1 minus Q, and the expected payoff or expected loss to player B when the player A adopts the strategy A2 throughout the game would be 10Q plus 15 times 1 minus Q. Therefore, player B should select the strategy Y 1 minus Y for whatever strategy the player A adopts, such that these two conditions are satisfied. Again, solving these as equality, we get Q is equal to 0.4. Therefore, 1 minus Q comes out to be 1.6. Now, the expected gain to player A is calculated by the value of the game is determined by substituting the value of P or Q in any of the expected value as given below. These comes out to be 13 after substituting these values. Thus, the value of the game is equal to the expected gain to the player A or expected loss to player B. Now, let us discuss the shortcut method. An alternative method for this algebraic method. If the original game consists of a payoff matrix of order 2 by 2 and there is no saddle point in it, then the strategies to which each player would resort can be determined as follows. Let the original game be this is first step 1. Subtract the smaller payoff in each row from the larger one and the smaller payoff in each column from the larger one. Consider the original game. Subtract smaller payoff in each row from the larger ones. 25 minus 5 is 20, 15 minus 10 is 10. Similarly in columns, 15 minus 5 is 10. After substituting these values, we get this. Now second step, interchange each of these pairs of subtracted numbers found in step 1. These are the values. After interchanging 5 and 20, 15 and 10. Now next step, put each of the interchanged number over the sum of the pair of numbers. That is 5 divided by 20 plus 5, 20 divided by 20 plus 5. Similarly 10 by 10 plus 15, 15 by 10 plus 15. Now next step, simplify the fraction to obtain the required strategy. We get this 0.2, 0.8 for player A for each of its strategies, 0.4, 0.6 for player B for both of its strategies. Expected value, now let us consider another example. Again, subtracting the payoffs. We get these, interchanging the pairs. Now putting the pairs over their sum, and on simplification, we get these values. Therefore, the strategies A1, A2 for player A are 10 by 17 and 7 by 17, and for the player B, the strategies B1, B2 are these, and accordingly the value of the game comes out to be 2 by 17. Now let us consider the payoff matrices of order m by n, 2 or 2 by n. If the payoff matrix is not of order 2 by 2 and there is no saddle point in it, then it can be solved with the graphical method. However, a game of m cross 2 or 2 cross n order can be solved by considering game as being subgames, each of order 2 by 2, because the players x or y can choose to play any two of his rows or columns as the case may be. The method of subgames is illustrated in this example. Let us consider a game of order 4 by 2 with the following payoff matrix concerning two persons. There is no saddle point in the game. Moreover, since player B has got only two alternatives to play, the player A will also use two strategies. Accordingly, player A can actually think of this 4 by 2 game as being of 6 subgames, each of size 2 by 2. The 6 subgames can be described as, the first is with A1, A2, second subgame with A1, A3, third subgame with A1, A4, fourth subgame with A2, A3, then this subgame with A2, A4, and then one more subgame with A3, A4. Now we solve the 6 subgames by pure strategy, or in the absence of the saddle point by mixed strategy shortcut method. Solving subgame 1, we get these values. Now solving subgame 2, we get these values. Solving subgame 3, there exists a saddle point. So, and the value of the game is the value of the payoff in the matrix. Solving another subgame, again there is a saddle point and the value of the game is -4. Solving the fifth subgame. There is no saddle point in it and the mixed strategies are calculated as this. Now subgame 6th with A3, A4, again there is no saddle point in it and the mixed strategies are calculated as given here. If we look at the values of all the 6 subgames, we find that all of them are negative. That is, the player B wins and player A loses in all 6 subgames. Thus, the player A would like to play the safest and accordingly he would choose that subgame which gives the maximum value of all the 6 values. That is minus 3.6, minus 3.87, minus 6, minus 4, minus 3.57, minus 3.82. Accordingly, player A would play subgame 5 whose value is minus 3.57 and the strategies for A and B would be 0, 6 by 7, 0, 1 by 7 and 3 by 7, 4 by 7. In this video, we have discussed a game without a saddle point and hence the game with mixed strategies. Defined the mixed strategies and the expected value. Solved the game with mixed strategies by algebraic method. Thank you.